Так, слышно чего-нибудь?
Да.
Мгм. Да, Саш, я получил письмо про то, что можно это переформулировать как-то, но ничего не понял. Может быть, вы мне как-нибудь объясните, что именно и куда надо переформулировать, чтобы это сошлось.
Ну да. Надо будет объяснить.
Надо. Привет.
Я, конечно, надеялся, что я написал все понятно.
Нет, но это не вы виноваты, а я ничего не понял, так что не волнуйтесь. Но...
Добрый вечер.
Добрый вечер. А на экране видно доску?
Да.
Да, хорошо.
Добрый вечер.
Добрый вечер. Ну что,
Добрый
у нас
вечер.
нету иностранных товарищей, и можно это самое.
Не, ну вроде Томаш хотел, сейчас может.
Ну давайте
соединиться.
тогда.
Я, конечно, не отвечаю за него.
Нет,
Вроде шла речь о том.
это самое.
Ну и вообще для записи, может быть, можно лучше по-английски говорить.
Ну давайте. Нет, вы как думаете, что это кто-то будет слушать? Ну, можете себе представить.
Ну, вот опять же, например.
Хорошо. О. So, Bruna, can you hear us?
Yes, I hear you.
Yeah. So there is now it's a valid reason to switch to English. Or maybe you already learned Russian, no?
I know the topic more or less, so I can try. I'm taking courses again.
No.
No, if there is a chance to understand in Russian, it's now. Мы можем говорить по-русски.
Tu penses nous pouvons parler en russe? Okay.
Добрый.
Хорошо. But still, I think it is, I want you to solve the problem, so I want to create the optimal conditions for that. Okay, so should we start now?
Yes.
Okay, so let me say some general things. So there is a very well-known old story that there are three worlds. There is a Shen world, there is a Kolmogorov complexity world, and there is combinatorial world. And there is some way to translate different statements from one to another. It's not automatic. Sometimes you need to. Sometimes there are general results like Romashchenko theorem about inequalities. Sometimes you just take a specific result and find the translation. And what would be fun is to prove some combinatorial results using Kolmogorov complexity. So this application of Kolmogorov complexity are sometimes most of them are nice, but there are still some version of counting or probabilistic argument or something like this. And it's quite rare when you can apply when you can get some non-trivial translation, which cannot be explained in combinatorial language. And once I think we achieved something like this with Vereshchagin and others, with this splitting of multidimensional set into almost uniform parts. But still, in this case, the complexity statement was quite simple. There was a non-trivial translation, but still the initial statement was simple. And now there is some example which, when the complexity statement is quite non-trivial, the proof requires several tricks, and so it's quite difficult I don't see any way to translate it directly. But on the other hand, the combinatorial statement is rather simple, and it's hard to believe that you cannot solve it combinatorially. So one of the goals is to explain this combinatorial statement, and then maybe some participant can explain why it's true without going to complexity. And now the question: should I start with this combinatorial statement, or should I start with how you come to it from complexity?
I guess from complexity.
From complexity.
That's
Okay.
my opinion.
So there is. Let me start with original things. So there is a communication and information. Communication information complexity. So let me explain the settings from the beginning. So we have Alice and we have Bob, and they have some random input X and Y, and they run some communication protocol on them, and so on. And finally, they get pi. This pi is transcript. Why it doesn't want to write? Oh God. Stupid. It stops working. I don't know.
No, it works, but slowly.
Slowly, but no, it's Zoom that should work more or less immediately. Okay, let me reboot restart the Jamboard. Okay, so it's let me check again. So there is a protocol pi, which is a function of X and Y. And there are two notions. So they are random on some space, common space, and pi is defined on the same probability space. And there is a notion of communication information complexity. There are two notions. There is internal complexity and external complexity. And okay, again, it doesn't want to write. So external complexity is just what the external observer. What is happening? Why it doesn't want extremely slowly?
Sasha, Can you provide the link to the Jamboard?
Jamboard, okay. No, but the problem is with Jamboard, it doesn't want to okay, so this I will.
But rebooting helps. So probably you just may restart your browser.
Restart the browser. Okay, so let me where is here is paste. Okay. So external complexity, what the external observer knows about XY. And internal complexity is what Alice, who knows X and pi, knows about Y. Okay. No. Okay, let me indeed restart the browser because it's something completely I cannot understand what is happening, but let me.
We don't hear you.
Your microphone is turned off now.
Yeah, can you hear me?
Yes, yes.
Yeah, so the internal complexity should be what Alice knows about Y and what Bob knows about X after running the protocol. And there is a well-known inequality saying that internal complexity is smaller than external complexity. And this we can draw in our standard way if we have X, Y, and pi. So internal complexity is X pi given Y. So information X pi and Y. So it's these three parts plus these three parts. Y pi given X. So this is this, and this. Yeah. Y pi given X. And external complexity is pi of XY. So it's yeah, what Alice knows about Y, what Bob knows about X, and what the external observer knows about X and Y. And so the difference is strange. Why it's 2?
I don't know. I think there's something wrong here because we want to show that external complexity is bigger. But if X and Y are, I mean, like external complexity is the most to the length of pi. So if pi is nothing, then
so but what do I do wrong?
You have to put X into the condition of the mutual in the first line on the first line when you define internal complexity.
Yeah. Of course, it's stupid. Yeah, it's my fault. So Alice, internal complexity. Okay, let me erase these wrong things. So internal complexity is with condition X how much Alice knows about, sorry. And how much Bob knows, this is right, yeah? So internal complexity, P, so it is this thing given X and pi of X given Y. Yeah. So this inequality essentially means that this internal part, this one, oops. Yay. What is happening? Why doesn't something is terribly wrong with it?
Or do you write somewhere else? I don't know, on Zoom. Then it's better or no?
No, it's probably better, but I still hope that maybe one can it's some intermittent problem, so we can start this. But anyway, this inequality means that the information, this triple information, which is this part in the middle, is positive, because blue should be bigger than green, so the additional thing, which is blue but not green, should be positive. And another way to solve this is just the entropy of pi is greater than entropy of pi given X plus entropy of pi given Y. So let's see why it's the same. And entropy of pi is something like this. So this. Oops. And entropy of pi given Y is entropy of pi given X, which is this, and pi given Y. So it's Y. No, it's pi given Y, and pi given X is this. And also, what is important, that in our setting, P is a function of X and Y. So this is 0. We don't care about this thing. And so again, blue is bigger than green, means that the part, when they differ, the blue one, the center one, is positive. So this is standard thing. So there are three things, three inequalities. Okay. What is he doing? So this first one, a second one, and third one are equivalent. So this is all what we need to do from the to know from communication. No, not all. So there are two ways to prove the setting, and one of them is inductive. So we can start a protocol as a sequence of message, and we can add one message one by one, proving this 1, 2, or 3 the same. But also there is a kind of theorem, which is, I think, Romashchenko, Kasset, Vereshchagin, I don't know, Kolya maybe knows better. And the theorem is more general. The theorem, let P be a, how to say it, rectangular function of X and Y. So there are two random variables, X and Y. And a rectangular function means that each preimage of each value of pi is a rectangle, combinatorial rectangle, a product of two sets here, something like this. And then we have the inequalities 1, 2, or 3. So communication complexity is somehow less general, because the communication complexity pi is obtained by first by dividing one coordinate, then by dividing the other coordinate. And here we have a more general statement, which it's not necessarily obtained. So in this picture, can be obtained, but we can have something like standard example no. What is it? Sorry, something is wrong with my setting, but
Meanwhile, maybe you can explain
it doesn't.
why what's happening in communication complexities case. What are we dividing, and why is this rectangular or whatever? I can't hear anything.
I can hear you, Sasha.
I'm afraid Sasha Shen's internet connection, something is wrong with it.
Yeah.
But I was out for 5 minutes, I guess. Can you repeat? He claims that 1, 2, and 3 are equivalent.
Yes.
1 and 2 and 3 are equivalent when pi is a function of x and y.
Assuming that pi is a function.
Yeah. And the theorem is that when it's a rectangular function, that they are true. I mean, these three statements are equivalent for whenever pi is a function, and they are true when pi is a rectangular function.
And do you have a link to the Jamboard?
Link to what?
It is in
To
chat,
Jamboard.
I assume.
Because I have
I will send it in chat now.
Okay. At least I can see the Jamboard.
Excuse me, once more, which function is rectangular?
Pi is a
Pi is a protocol function, so it consists of all the bits that player send to each other. So it's just, if you consider communication protocol as a tree, that's just a path in this tree, saying that like
Yes.
0, 1, and so on. So, and also you can think about it as a function that outputs the leaf of this tree, because the leaf is has one-to-one mapping to the path, but it's a tree, right?
Oh, I see. Thanks.
And this picture with 3 circles explain why 3 is equivalent to 2, I guess.
Why 1 is equivalent to 2? Okay.
Why 1 is equivalent to 2?
Also, why 3 is equivalent to 2? Because in 3, you can see 3 blue points, which corresponds to h of pi. And you can see also 2 green points. One green point for the complexity entropy of pi given x, another for complexity of pi given y. And you see that one blue point is not covered by a green point, and so the inequality means that this green point is non-negative.
This blue point, I guess.
This blue point. And this blue point is just what is in the left-hand side of equation inequality 2.
Yes. Yes, I think that's it.
And probably it's the same for 1. So the common information between pi and the pair xy consists of 3 blue points. And 2 green points correspond to 2 terms in the in the right-hand side of this inequality. Right. Now it's clear that all of them are equivalent, assuming that pi is a function of x and y.
Yeah.
Okay. So I guess, have we understood already why for rectangular functions all these inequalities are true? I know actually why it is, I guess. Sasha,
Yeah, I guess there is a proof, a specific proof for protocols, and a general proof that works for any functions, rectangular functions.
I know the general proof. It's in our paper, Romashchenko, Kasset, Vereshchagin.
That actually what Sasha said, that you know the authors and you can correct him if he is wrong. It's on the left, Romashchenko, Kasset, Vereshchagin.
So how we prove 3? We prove 3 first assuming that x and y are independent given pi.
Yeah. So I hope I can say something now.
Okay.
So what I wanted to say, that the theorem is more general than the previous for communication complexity, because you can have a rectangular division like this, which cannot be obtained by any communication protocol. So this is more general statement. And then the proof, as we started saying, that we have pi x and y, and pi is a function of x and y. And now we consider new variables, pi, x prime, and y prime. So first we take pi with the distribution it has, and then we take x conditional to pi and separately y conditional to pi. So this is a standard trick, making 2 variables artificially independent given the 3rd variable. So
can you share the Jamboard now? Or
yeah. Okay. I'm terribly sorry. Okay. So no, why it doesn't want to make a big Jamboard? Okay. Yeah, something like this. So can you see now something?
Yeah, now it's good.
You can see.
Yeah. So we make artificial independence of x and y given pi. So we start with the same distribution of pi, and then we add conditional distribution of x and also conditional distribution of pi, but making them independent. So everything which is related to pair pi x remains the same, and pi y remains also the same. But now x and y are independent given pi. This is thing. So first we take some rectangle according to distribution of the rectangle we have, and then we take x and y independently in the first and the second projection of the rectangle, just with the distribution they have if this rectangle is fixed. So we get some point in pi in this rectangle, but the distribution of the point is different. It's now independent. So for given pi, we have some conditional distribution. So we have somehow distributed things in x and y, and we don't know how. And now they are making artificially independent. And what is important, that in these new things, also pi is a function of of x, y, and x prime and y prime, because x prime and y prime are in the same rectangle. So we just look on the rectangle which contains them and get pi. So it's 0. So we have this and this. And now why we get this? Oops. Because this means that this can be replaced by pi given x prime plus pi given y prime, because the distribution of pi and x is the same as pi x prime. So it's enough to show this. But here we have an additional things that x prime and y prime are independent given pi, which means that this thing is 0. Then this middle part
is positive.
Is positive because it's just the entire thing.
Because so the sum is positive always.
Yeah, this new part is the same as in information x prime and y prime. And it is always positive. So here we have also 0, and now we have 0 also here. So this is a proof of Romashchenko-Vereshchagin theorem, Siemens, I don't know, theorem. And here is if it's clear, we can move, but let's see whether it's clear or not. So any questions about this theorem? No, Kolya, should we move or should
I guess we can move.
Okay, so now we want get this complexity version of this rectangular theorem, which is also somehow in Vereshchagin and in Romashchenko and Siemens paper, but it's kind of a there are some unnecessary rectangular thing which is not needed. Actually, for complexity case, we need only one rectangle. So there is some rectangle pi, and there are two strings, x and y, and we want to show, and pi is a rectangle, combinatorial rectangle, and we want to show that complexity of pi is greater than complexity of pi given x plus complexity of pi given y plus minus something O of log n plus some property of some thing depending on the pi. And what is this thing? So somehow before we use the property that rectangle, if we have a division, then rectangle is determined by average point. So we want to keep this property that rectangle is simple given average point. So we have to define I of pi, irregularity of rectangle pi, something as a minimum. Maximal complexity, sorry, maximal complexity of pi given xy taken over all things in pi. No, actually, it's not important that pi is a rectangle. So if we have any finite set A, we can define irregularity of A as maximum taken over all z in A, complexity of A given z. So we consider regular sets, which are sets who are determined by each its element. So if, for example, we have some kind of statistical classification we take all the elements which have the same, I don't know, mean or the same variance, and then of course every element of the set determines the mean or variance, and so determines the set. So this is a kind of a I of A small. They are kind good sets for statistics. And another question which I asked already, Kolya, that whether we can consider in algorithmic statistics, we consider model which are good sets. But it's kind of another story. We just are interested in a good set here. So this is the theorem of Romashchenko, Zeeman, or maybe somebody else. Yeah, and again, it can be proven using artificial independence. But now we want to use this independence. Now we need to use this artificial independence in Kolmogorov setting. And this can be done by Romashchenko's typization trick. Yeah.
Could you please again explain the statement? So pi is a rectangle. What does it mean?
Pi is a combinatorial rectangle in a product of, we assume that x and y are, there is a set of n-bit strings, so we have some combinatorial rectangle there.
Okay, and what does it mean that it is, okay, I see.
It's simple given average point. So if we have some communication protocol, fixed simple communication protocol, then every rectangle is determined by every its point, because we can just run the communication protocol on every its point and come to the same rectangle.
Right, the inequality is also for x and y that are from pi, right?
Yeah.
Not for all x and pi.
Yeah. X and y in pi.
Right, and do we assume that we have some kind of partition of all the space in these rectangles, or is there like?
No, this is important. Somehow now, like in Kolmogorov complex, usually when we switch from classical setting to Kolmogorov setting, instead of some general objects, we have individual objects. So here we have just individual rectangle. We can say that somehow we can say that rectangle is an element of a partition without saying anything about the partition. Instead of this, we require it to be regular, to have small value of this I.
Okay, I see.
Yeah. So let me say something about the typization trick, which is now classical, but it was invented by Andrei Romashchenko, I think, in his PhD thesis. So let me explain it in general setting. For example, if we take some string x, we can, instead of considering this string x, we can consider all strings x prime with complexity smaller than x. So somehow we include x in some set where x kind of typical element. Now this is trivial, but the less trivial things, if we have some pair, we now consider all pairs x prime, y prime, which have smaller value. All complexities are smaller. So the complexity of x prime is smaller, the complexity of y prime is smaller, the complexity of pair is smaller than conditional complexity of y given x. What? Condition complexity of y prime given x prime is smaller than, and everything like, no, that's all. There are no other non-trivial quantities. So, but the idea is again xy is one of the elements, so we get some kind of set when xy somehow is a typical element. This is the idea. And here now we can do this the same. We make fixed pi. For fixed pi, we make some x replace x prime, replace x by some typical x. We consider all x primes such that pi is, for example, pi is some product of some x times y. So we consider all elements x prime which have complexity smaller than complexity of x, complexity of pair x pi is smaller than x prime pi is smaller than complexity of x pi, complexity of x prime conditional to pi is smaller than the complexity of x conditional to pi, complexity of pi given x prime is smaller than conditional to pi given x. Do I forgot anything? X prime, and all the pair and all the conditional complexity in both directions. And the question is how big this set is. So we have this condition which says that log size of this set is at most complexity of x given pi, because just the set we have all these requirements. And what is the crucial Romashchenko observation is that here we have equality. So this is a main observation of Andrei. So why we have equality? Imagine the set is smaller, but we can enumerate all given pi. We can enumerate and numerical constant. These are just numbers. So if we know these numbers, we can enumerate this set. And x is an element of this set. And so if the set is small, then we can just, all its elements should be simple given pi. And x1 is one of the elements. So x1 would be simpler than it is. So the set should be large. As large as it should be in this thing. So log size is exactly the complexity of x given pi. Is it clear? So this is a very, very crucial moment. So this should be clear.
So log size of this set of all the elements that is smaller is exactly the complexity.
Yeah, first it cannot be greater than the complexity because we
well,
have
not exactly, up to logarithmic terms.
Up to logarithmic terms.
That might be confusing.
Yeah, up to plus O of log n.
Right.
Now the property of pi to be regular is not important. This can be done for every rectangle pi and its element point xy in it.
Actually, if you want to be precise here, I guess you need to add this I of pi, I mean, this regularity parameter.
No, why?
Because you have here the complexity of x and pi.
Yeah.
And unless you're saying something, this complexity can be, can be exponential, right? Because it's a subset of an exponential set.
Why the complexity of pi is not big? So we need the complexity of pi indeed. We need the complexity of pi is b of, I don't know, O of n, for example. it's guaranteed if pi is regular, because pi is determined by every its element, and so we can have O of n. But really we need the pi not to be extremely complex, so it should be in a reasonable set.
So you have to add I of pi here there.
Not I of pi, I have to get log C of pi, or assume that C of pi is O of n, which is automatically guaranteed if pi is regular.
Sasha,
Yeah.
Zachinsky said that pi is regular means that I of A is small, I of pi. But
Yeah.
how small? I of pi is of order n, right?
No. In our theorem, we will allow something like this. So
Okay.
if I of pi is of order r, it doesn't matter. It's nonsense. It's trivial. So what we want is to be that I of pi is also of logarithmic order. This is a typical case.
Well, so we assume that I of pi is logarithmic, or we don't assume that.
No, now we don't. Okay, it's easier to assume, but no. No.
No, you can just state the theorem when you additionally assume that I of pi is constant or whatever. But if you don't do that, then please...
The theorem is true as is. The theorem is like this.
Yeah. But now we are proving a weaker version where I of pi is constant or whatever.
No. It's not. There is no problems here. Just we want to prove the theorem, and what I'm saying that we may assume that C of pi is O of n.
All right. Why we can assume that?
Because in our theorem, C of pi in general it is smaller than I of pi plus O of n, because pi is determined by its points with complexity I of pi.
Mm-hmm.
So if complexity of pi is greater than n, then this is trivial, because we have this I of pi is also greater than n, and we have just trivial statement here.
Mm-hmm.
So
yeah.
Yeah. So sorry. It's really not important. But if you want if it creates problems, you can assume that I don't know, if I of pi is O of log n, then we can just assume this, and then we can delete this I of pi. And complexity of
let's
pi
assume that I of pi is O of log n.
Yeah, but this is really it's not needed. But okay. So what I was saying is just a general thing. So we make a thing which is called a typization. So we switch from some point x to the set of all point x prime, which are the same as kind of behave a form of all points like x, or simpler. And what I'm saying, that by definition, the number of this x prime, the log size of this set, is bounded by this C of x prime given pi. And if complexity of pi is O of n, then the log size is exactly C of x pi plus O of n. Because if it's smaller, if the size is small, then every element can be described by the ordinal number in this set. And so the complexity of x should be smaller than it is. This is the main thing.
So you mean that X itself can be.
Yeah, X itself is one of the element. It can be determined by its ordinal number, and the ordinal number is of log size. Its size is log size of the set. So if log size is smaller, then C should be smaller, and then it was.
Yeah, and we can enumerate this set by running, because all the inequalities with x prime is always on the left hand side where it's smaller, so we can.
Yeah,
right,
yeah.
And
sorry.
And the right part is always just some number. So
some number, yeah. And of course, we need to know what Sasha was saying and what was correct. For enumeration, we need to know pi also. So
yeah.
If complexity of pi is very large, then we logarithmic terms in these inequalities will be logarithms of this very large number. But we don't want this. Okay, and what can be said also about this what we achieve by this? We claim, so for most elements of this set, let us call it X prime, I don't know. Most elements of X prime, most elements X prime, small in X prime. Of course, we know that for most elements, since it's of log size, the complexity of X prime given pi is the same as complexity of X given pi, because we just have that many elements. And so the complexity of the pair X prime pi, which is the complexity of pi plus complexity of X prime given pi, is the same as complexity of pi plus complexity of X given pi plus, so which is complexity of X pi. So also with the same precision. So conditional complexity is the same, the complexity of pair is the same. And this implies, sorry? For most elements X prime, for a random element of X prime, for most element of X prime, we have this inequality. And also, since we can write something like in other direction, the complexity of pair X prime is the complexity of X prime plus complexity of pi given X prime. And we know that it is the same of complexity of pair X pi, which is equal to complexity of X plus complexity of pi given X. So we know that by construction, these things are smaller. We constructed our set of all X prime such as complexities are smaller than the complexities for X. But the sum, for most of them, the sum should be the same. So the only way to get this and to get equality in both terms, if we decrease one term, we decrease the sum. So most elements this prime have the same complexities related to pi, I would say like this. So we start with some X and we get some X prime here. And also we can independently get some, not independently, just repeat the same construction and get some Y prime here. And now what we achieved, we just can take this artificial independence now. What do? We say that for most pairs X prime, Y prime in this new set, so what we have, complexities, complexities of x prime related to p, related to pi, are the same for as they are for x. And also for most pair, the same is true for y. Complexity of y prime related to pi are the same for as they were for y. Now also complexity of pi given x prime y prime is at most the irregularity of pi, because it's just point in the same set. And also for most of them, complexity of the pair given pi is just the log size of the set of all pairs, and the log size of the set of all pairs is as a product, so it's just complexity of x prime given pi plus complexity of y prime given pi. So for most pairs, we have all these things. And this is exactly what we have for random case. So we now, instead of xy, we take a typical pair in the set x prime y prime, and we see that we can replace here x y prime. So we need to prove this. It's enough to prove it not for x and y, but for x prime and y prime. And for x prime of y prime, we have additionally this independence property. So we repeat the argument we did for again, we draw the picture. Now we draw complexity picture. We have x prime, y prime, and pi. And we also have, we compare it with x, y, and pi. So we know that here we have a zero, not zero, but it's small because it's smaller than I of pi in both cases. And for x prime and y prime, this is almost zero. It's small. And so it's we may assume without, and we need to show again that this triple thing is positive. And so this triple things for x prime and prime is positive because it's just the mutual information of x prime and y prime. This triples thing. And all the things, three things are, they never combine x and y. So they are the same for x prime and y prime as they were for x and y. So we can just prove it for x, y, and x prime and y prime instead, and this is the same. Okay, so this somehow finished the proof of Romashchenko-Zeeman theorem. Is it clear or not? Kolya, say something. Okay. Let's now try to look on the combinatorial meaning of the theorem. Let me just write what it says. We have xy point, and it's in some rectangle pi, and complexity of pi is greater than complexity of pi given x plus complexity of pi given y. And let me try to prove a combinatorial. Let me try to prove the statement combinatorially. I claim that it will be okay. So one of the ways to prove it like this. So if C of pi is represented.
Wait a moment. You want to prove this theorem without that I think I of pi, the inequality.
You assume that it's logarithmic.
No. Let's prove the theorem if pi is a rectangle of a partition. Just return to our initial setting for simplicity of a simple partition containing x and y. So we have some kind of protocol or just a partition into rectangles, and pi is just a rectangle which contains x and y. And what is the combinatorial standard way of combinatorial proving this? It's enough to show that if we have represent the sum as k plus l, that either complexity of p of x smaller than k, or complexity of pi given y is smaller than l. No, it's just a standard way. So a is equal to more greater or equal to plus c if for every k and l such that l is a is equal to k plus l, then b is smaller than k or c is smaller than l. And we can even write like this to be more uniform. Also equivalent. So what it corresponds to combinatorial meaning? There is we can enumerate all rectangles pi or partition rectangles which have complexity smaller than k plus l.
Well, if you assume that they come from a simple partition, then you can just compute this partition.
Then they are disjoint. Enumerate 2 to the k plus l disjoint rectangle.
Sorry, I don't understand. So you assume that we have a simple partition, meaning that we can compute it, right?
Yeah. If we have a compute, we can compute the partition. So
we can compute the partition, and then we can just and then we enumerate.
When you enumerate elements of this
partition that have complexity at most k plus l.
Yeah. So of course there can be much more elements in the partition. They not all have complexity smaller than k plus l, because the partition can be just partitioned into singletons. So the partition is complex, long, big, simple but big. So, but we enumerate at most 2 to the k plus l disjoint rectangle, and then somehow this means that either this is small or this is small. And this is small means that if we have x, there this rectangle is, there are few rectangles that intersect this vertical line. And this means that there are few rectangles intersecting this horizontal line. Okay, I am trying to motivate the game, but maybe it's a bad idea. Let me explain the game. Yeah, as Andrei Muchnik liked to say, there are two players, nature and mathematician. So nature enumerates rectangles disjoint at rectangles in Bn times Bn. And mathematicians, after n gives a rectangle, also the game has parameter n, k, and l. After n gives a rectangle, mathematician declares this rectangle, classify it just as a label. Again started as horizontal or vertical. And the number of rectangles is at most 2 to the k plus l. Okay, it again starts to lag. What?
I can write for you, actually, I guess.
Okay, so the number of rectangles is bounded by 2 to the k plus l, because it corresponds to the bound for complexity. So can you write for me?
All right. One moment, please. So page number 18, right? No.
No, page number 4.
4. And I guess the next item is like that. The number. Can you see what I am writing?
Yes.
The number of h rectangles is at most 2 to the k. And the number
on every horizontal line.
Number of v rectangles vertical is at most 2 to the l. And the claim is that actually mathematician can win somehow this game.
But I mean, the number of
horizontal rectangle intersecting every. No, I cannot write anything.
It cannot be
the
like
number
that
of horizontal rectangles intersecting every horizontal.
Every horizontal line.
Every horizontal line.
Every horizontal line has at most h rectangles, and every vertical line has at most v rectangles.
Right.
At most 2 to the l v rectangles, and at most 2 to the k h rectangles.
Vertical line, any vertical line.
Could you please share the link to Jamboard one more time?
Link to Jamboard. Okay.
Actually, I guess I can even share it. Let me share.
Yeah, maybe it's better if you share, because then it's.
So I need to share.
No, I have sent the link. So you need to go to page 4.
4, okay, this one.
Yeah.
I see my own writing.
Yeah. So the game is just very simple. You have this rectangle. So nature provides some rectangles as it wants. They should be disjoint. And you should declare them as horizontal or vertical. And what is bad, if your horizontal rectangles are more, there are a lot of them horizontal on the horizontal line. So if you have a lot of rectangles like this, you cannot declare them horizontal. They should be vertical. And if you have a lot of rectangles on a vertical line, they should be horizontal. And the last thing is we just allow here some polynomial of n factor, because it will have a logarithmic term in complexity.
And what's interesting, I said you, that without that polynomial factor, it is false.
Yeah. So just now we can forget about all this complexity things and just speaking about the game. First, in offline setting, so if all the rectangles are given in advance, mathematicians can win.
With poly of n factor.
Without poly of n factor.
No. Do you recall my example?
No. Okay, say your example.
Okay, let's switch to page number 5.
Yeah.
So we take the chessboard, we divide it like that and like that. Instead of 2 to the k, we will 3 actually. I mean, and 2 to the l will be also 3. And so
no, okay, so that's very good, because we can just declare all rectangles to be horizontal, because every horizontal line crosses at most 3 rectangles.
Yeah.
but what's the total number of rectangles
It's
here?
8.
8.
So you have one
I'm-
more.
I'm
you
sorry.
can add one more rectangle, which will make 0, make
So
9.
8 equals to, say, the square root of 8 times the square root of 8, right?
Yeah.
And now we want to declare some rectangles horizontal, some of them vertical, so that every line intersects at most square root of 8, which is actually impossible.
No, okay, square root of 8 some nonsense, but it's not a problem, because you can declare this thing's vertical, and this thing's horizontal.
It's possible when you divide into 2 parts, vertical and horizontal.
Yeah, of course.
I see.
That's entire business.
Because
if we don't divide into parts, we can just make no.
It's not easy to come up with such a counterexample.
No. Just make many rectangles like this and many rectangles like this. So we have 2n rectangles, and if we don't, and we have n rectangles here and n rectangles here, so it's n square. So we have much less rectangles than n square, and still we have n rectangles which intersect horizontal line and vertical line.
I see.
The entire business is then we can declare all this vertical and all this horizontal. And then we get very good parameters like 1 or 2. So I can even explain, as Sasha Kazachinsky noted, that offline case, mathematicians wins easily. Why? We have many rectangles. There are two. Let's denote.
Sasha, and in this offline case, and also in online case, it's not important that k and l are powers of 2, right?
No, it's not important. It's even if it's better not to assume them. So we have KL is a product of 2k and 2l. And so we have at most k horizontal intersection and at most L vertical intersection. And total number is KL. So if we have at most KL rectangles, we can classify it as horizontal and vertical. So we have at least K horizontal intersection for horizontal rectangle and L vertical intersection for vertical rectangles. So how mathematician easily wins? Just very simple. If every horizontal line cross smaller than K rectangles, there is no problem. We can declare all the rectangles horizontal. Trivial. So we can assume that some horizontal line crosses at least K rectangles. And then we declare these rectangles as being vertical. Some line crosses at most K rectangles. We declare them vertical. And we have now KL minus K, which is KL minus 1 rectangles. And so we can apply our argument by induction, and for the remaining we have K horizontal or L minus Y vertical. And this our deleted rectangles just add +1 vertical rectangle, because they are vertical, they horizontally they are disjoint, because the same line crosses all of them. So their horizontal projection are disjoint. So every vertical line can cross only one of them. So this +1 is now allowed because we have KL minus 1 here.
Very clever.
No, it's Sasha Kazachinsky who is very clever. So
I meant that the proof is clever.
Yeah, but Sasha is not bad either. Okay. So for our offline case, it's mathematician easily wins. But for online case without polynomial factor,
it's impossible.
now nature wins. So if we can take n very large if we don't have polynomial factors.
I guess we should see page number 6.
Page number 6, sorry. Yeah. And this I asked the students in Kulikov. Sasha Kulikov has organized the university on how to say it, Cyprus. He organized a university in city called Paphos, and there are some very good students, which are Russian students who flee from the Russian dangers.
No, he didn't organize a university, just a program.
No, he organized actually. There was some university, something like Business and Tourism University, or just some strange university. And he and not he himself, the company JetBrains, who moved to Cyprus, also supported this thing, and also Borya Muzakansky and his IP on Web company supported this thing. And so there are about 40 students from Russia, and some of them very good. And two of them, which Ilya Kondakov and Misha Yarashevich, when I asked, he explained me that online case you cannot win. Nature can win.
So and why is this?
The strategy for nature, so we take a very, very big rectangle. square, very,
Will
very
be
big
something like
square.
Ramsey theorem now.
Yeah. So we divide it into 4 parts. And we declare, first nature takes this rectangle, this 1/4. And of course, we can declare it horizontal or vertical. So imagine we declare it as horizontal. And then all the following game will happen only in this square. Oops. Only in this square.
And otherwise in the left upper.
Yeah.
Square.
If it's vertical, then we go here or here.
And the upper right is not used.
The upper right is not used in never used. So what is the thing? Why it's important? Because if we have a game in the square, every line will have one horizontal intersection. So by adding this square, we have horizontal count plus 1. We just add 1 to horizontal count for sure.
Yeah.
And then nature repeats the things. It chooses some square here. And for example, we declare it vertical. Then the nature decides that all the following game will be played here. And so after if we have k plus l plus 1 steps, which is much less than kl, which we are allowed to do, we have total number of horizontal and vertical intersections will be k plus l plus 1. Because every step adds either one vertical or one horizontal count. And so and this is much smaller than KL. So we're forced to exceed either horizontally exceed K or vertically exceed L by using only K plus 1 plus K plus L plus 1 steps instead of KL allowed. So our goal is not achieved.
Sasha,
is it clear?
But doesn't it break the initial claim about that mathematician wins if we allow polynomial factors?
No, because these rectangles are exponential in this capital K and L, which are itself exponential and n possibly. So here the log of the rectangle is polynomial in big K and L.
What do you mean? What is exponential? The size of rectangle?
The size of rectangles.
Let's
important,
see. So
important which is the size of rectangle. I mean, in this combinatorial setting, we allow polynomial factor in the log size of rectangle, right?
Yeah, and here log size is of order K and L.
I see.
Capital K and L, which is the number of forbidden intersections and so on.
Moreover, online case with polynomial factor can be won, and this is our main observation. Game with polynomial polyos and factor
Sasha, is it
Page 7.
page 7?
Mathematicians wins. So this is our main theorem. And
so
also,
you assume that the total size of the chessboard is 2 to the n, right?
yeah, so we have, initially we have 2 to the n times 2 to the n. And we have k and l parameters, which are also polynomial in exponential in n. No, they are obviously exponential in n because we have only 2 to the n times 2 to the n points. So KL are smaller than 2 to the n, 2 to the 2n. The product is smaller than 2 to the 2n.
So
And
nature in an online manner enumerates rectangles k times l, and the mathematician classified them also in online.
yeah, so nature gives rectangle one by one, and mathematician classifies them. And the total number, there are some parameters. Let's assume that they are 2 to the k and 2 to the l, because we have, since we have polynomial factors, we can assume that they are powers of 2, because if we change it by 2, it doesn't. The game is still okay. And the claim is the mathematician wins in this game. And what is my challenge for you? To prove this without complexity.
So do you mean that you have a proof without complexity?
No, I don't have a proof, and I don't know anyone who has a proof without complexity. But what I have a proof with complexity. And that's probably the final thing I can try to explain today.
But maybe Sasha Kazachinsky already has the proof.
No, I don't have a
No,
proof already.
okay.
I
So
just have an equivalent reformulation in terms of predicting with experts.
Yeah, it's something which I don't understand yet, so I would.
And I mean, and then there is a hope that we can use technique from experts to show this.
Oh God.
Combinatorial.
Okay, but let me show you the proof with complexity. So it's very simple. So imagine mathematician cannot win. So then nature has a winning strategy. Also, we can assume that if we take the first winning strategy, the strategy is of complexity O of log n, because all the parameters k, l, and n who define the game have logarithmic complexity. So if there is a strategy, we can find the first strategy by some search, and it will be simple. It will be of complexity O of log n. Yeah.
So in this online formulation, the sequence is kind of like fixed by algorithm, but it is not known to the mathematician.
No.
Right?
No. We consider the game. The sequence is not fixed.
So what is the difference with this adversarial?
No, the game is just now the players make move. They alternate. So nature provides a rectangle, mathematician classifies it. Nature provides another rectangle, mathematician classifies it, and so on.
So what is the difference with this counterexample that you showed?
A counterexample is because we allow poly of n factors.
Okay.
In the counterexample, it couldn't be put into the overall rectangle size to the n times 2 to the n.
Yeah, so for this counterexample, we need to start with a very large rectangle. So actually, it works only if k and l are very small, are logarithmic. And this polynomial factor will cover this.
Okay.
Yeah. So imagine imagine mathematician doesn't have a strategy. Then nature has a strategy. Then nature has a simple strategy, because simple in terms of complexity, because we can just consider the first strategy in some order. So this winning strategy will have small complexity. And let n play the strategy against kind of basic strategy for M.
Blind strategy.
Kind of blind strategy for it's not exactly blind, but let me say what is the strategy. So nature gives some rectangle, and we say that rectangle pi is horizontal if the complexity of pi given y is smaller than k for all y in the second projection of pi. And p is vertical if c of pi x is smaller than k for all x in the first projection of pi.
Smaller than L.
Smaller than L, yeah. So why it's good? Because horizontal rectangles, if we have many horizontal rectangles and some line which intersects them, all these rectangles have complexity bounded by k, given this y.
Sasha, before proving that this strategy wins, you need to prove that one of these following cases holds.
Yeah,
right?
sure. But what I want to say that if one of these cases holds, then the strategy will win.
Okay.
Just because actually we should add some c log n here, and still the strategy will win, because for every y, for every horizontal y, if it goes on the level of y, then maybe there are some horizontal rectangle which intersects them. But since they are declared in this way, they all have small complexity given this y. So there cannot be many of them. So there can be only intersecting rectangle. We can only 2 to the k times poly of n. So somehow this strategy guarantees small intersections. What is not guaranteed is that one of the cases happens. So imagine that mathematician with this basic strategy is stuck at some point. What does it mean? That we have some rectangle pi. So this is not true. So there exists some y. That complexity of pi given y is greater than k plus c log n. And also the complexity of pi given x is greater than L plus c log n. And complexity of pi is smaller than to the k plus L plus O of log n. Because
without exponentiation, Sasha.
Yeah, sorry. Because in total we have 2 to the k plus L rectangles. Our game has the length 2 to the k plus L. So the complexity is smaller than k plus L plus O of log n. And also, complexity of pi given xy is of order log n. Because we have a simple process and of enumerating all the rectangles, and if we know xy, they are disjoint. So if we know xy, we can just wait until some rectangle containing x and y is enumerated. We use this simple strategy, and all this process is computable. So we have this. And also it's not only for xy, but for all x prime, y prime in these rectangles. Because the rectangles are disjoint, so the irregularity of A is O of log n. And so we get our contradiction. So this is big, this is big, this is small, and regularity is small. So if the constant C is large enough, we get a contradiction with our complexity theorem.
Can you explain it once again? So, like, if this is large, where's the contradiction?
Contradiction is we have theorem that C of pi is greater than C of pi given x plus C of pi given y plus O of irregularity of pi plus O of log n.
Yeah, okay, I see.
This was theorem from the previous part, and now we have complexity of pi is small, and complexity of pi given y and given x is big. And irregularity is also logarithmic. So this cannot help. So, and in this way, we finish the proof I think we just have we looked at, we have a complete proof now. We didn't miss anything. So we prove that in this game with polynomial of n factors, mathematician wins. And now the challenge for you is to provide the combinatorial proof without all these complexity considerations.
Okay.
Now you know that the strategy exists, and now can you show the 8th page? I can just draw some picture there. Finishing the last thing which I can say. So for parallelepipeds, for example, what do we have? We have complexity, the inequality is the same. Complexity of pi given xy plus complexity of pi given xz plus complexity of pi given yz. Or we can have another inequality which has factor 2 here, but complexity is only given one thing. So this can be proven also using Romashchenko method. And there is also a game. A game is now that the nature provides parallelepipeds, and we can classify in 3 directions: horizontal, vertical, and z direction. And this thing requires, in the first inequality, requires that every vertical, horizontal line or line in this direction crosses few of them, because we fix 2 coordinates. And the second theorem says that planes obtained by fixing 1 coordinate crosses few of them, but of course more than, because there is two. Then actually it's square of number of rectangles allowed. So this is true. This can be proven using for complexity, and so we get some consequences for combinatorial game.
Sasha, and under what constraint this inequality are true?
No, they are true just not with constraint, but with precision. Precision is O of log n plus I of p.
So we do not require that boxes are disjoint.
No, we do not require that boxes are disjoint. No, in our complexity inequalities, no. In our complexity statement, there is no boxes. There is just one box.
I see.
For game, we require them to be disjoint.
I see.
Actually, we can make a weaker requirement saying that, for example, for rectangle, they are maybe not disjoint by the multiplicity at every point is bounded by polynomial in n. So it's even a stronger combinatorial statement which follows from the complexity one. But just even if you prove without for disjoint box rectangles, it will be great. So I just say that after you find the strategy for mathematicians, then you can there will further questions how to make it 3D versions in two games for 3 dimensions, or for many dimensions. Actually, it's not really important. And the second question is how to adapt the strategy in case of non-disjoint rectangles with small multiplicity.
Yeah.
And so again,
the complexity proof is for this case also works.
Yeah, the complexity proof for this case also
multiplicity.
works.
Well, let's say if the constant multiplicity, then the same. Multiplicity is just how many. What is the maximal number of times an entry can be covered?
Yeah. So if there are polynomial many rectangle contains a given point, then the complexity of each rectangle given this point is logarithmic. So still everything is okay. So it's it would be too good to be true if we can prove if there is a combinatorial statement which can be only proven using complexity. It's hard to believe, because the complexity proof is quite funny and uses non-trivial tricks. And so if we get a combinatorial statement and it's a non-trivial combinatorial statement, we can be very proud of. So I guess some things are not so good, and there should be some simple combinatorial proof.
Or maybe not very simple.
Not very simple, but some combinatorial proof. So my request is to think about this and to invent a combinatorial proof. You can. So actually you don't need to know anything about complexity. Just there is a game, you are given rectangles, you should classify as horizontal and vertical, avoiding big intersections. So I guess there should be some kind of potential. We can somehow, if we have a rectangle which has a lot of intersections on the horizontal lines, we should call it vertical. And if it has a lot of intersection with other horizontal rectangles, vertical rectangles on the same vertical line, we should call it horizontal.
Sasha, sorry, no, you are saying about online version.
Yeah, online version.
That some rectangles may be classified up to the moment.
Yeah.
You should classify.
No, just the idea what kind of potential we can have. So we somehow are given rectangle, we classify them. And then we get a new rectangle. And we should decide whether it's horizontal or vertical. And the more vertical rectangle we already declared as vertical are on the same vertical lines with this rectangle, we should avoid calling it vertical.
I see.
And if we have a lot of horizontal,
you are trying to maintain a greedy balance.
Kind of balance to make something growing not too fast. We can make just something.
Maybe it works. I don't know.
No. I guess it should be like with our previous story with Newman and Alon.
But
so,
it is important that rectangles are non-intersecting.
Non-intersecting, of course.
Yeah, and so it might be that the strategy should take into account positions of rectangles, because if we
no, they are combinatorial. They are not nothing like positions.
Combinatorial, of course. But if you have a lot of rectangles, you have some restrictions on filling gaps between rectangles.
Yeah. No. I think that there should be some kind of continuous parameter which matters how close we are to the dangerous case.
In my taste, your complexity proof exploits in some way this structure, what is possible to put between many other rectangles. It's very informal. I cannot explain it in more clear way, but it's
no, of
it's
course,
my gut feeling.
The complexity proof somehow uses they are disjoint. It's important.
Yeah.
But the plan is just to have some potential measuring in some way how close we are to dangerous case. And then we should prove that this potential, whatever rectangle we are given, we can either declare it horizontal or vertical, not increasing the potential too much.
Yeah, well, they teach that you should take exponents of the number of intersections, so on, and then
or
take
something.
their sum. And
so I guess just the story with our other result, which we have a complexity proof, and then we show it to. There was some conference, and I asked the question, and the combinatorial expert being there, Newman and Allen, immediately invented some potential, and explained that we should just do something with this potential. So
well, just then ask Newman and Allen. Why are you asking stupid people?
But before
solution.
But they probably don't care. Yeah.
Before bothering great people in combinatorics, I think there is enough great people here to which are now already know this. So they should just think, for example.
How do you think Alan, for example, has like 50 papers a year? Like everybody asks him questions, I guess, and he answers them. So that's how he functions.
But it's more fun to solve yourself.
And then you will have a paper in a year. More papers in a year. Yeah,
but that's maybe a reason not to do it, because you have to write the paper if you invent the answer.
No, Alan and Newman didn't write anything. They just explained the proof, and everything was done for them. So I can promise you just invent the strategy, and I will write it down if it's not too complicated.
Okay, and but also I think there is some kind of a hint from the other proofs, because Romashchenko technique considers random strings, so it suggests we need to use probabilistic method, and maybe this potential idea will become that if a rectangle making vertical is dangerous, we will use lower probability or something.
Yeah. Also, you can construct a probabilistic strategy for mathematicians which has a positive probability of winning. Because if there is then it excludes the strategy for nature, so mathematicians wins. This is another interesting trick which was used in this by Vereshchagin in this game about Epstein's story and all this.
Yeah. So a lot of blah blah blah, but
Yeah. So there are
we'll
many.
see the very cool.
Yeah, so Bruno, yeah, I think you will just need some time and you will invent the strategy. So just game is simple, everything is simple. You should just invent the strategy, and you have no excuses.
No, but I promised many things. Like I need to write some lecture notes for the students, and then I do something with Huawei company, and I need to supervise some people, but I don't know. Anyway, I cannot do it soon. So if people fail in after 15th of January, I will think about it.
No,
There's some handicap.
Yeah, I didn't know what will happen.
So I will.
January,
No. Then so I need to work on my house and from 1 till 15th of January, and then I will return to Moscow, and then I will ask you, is it solved? Yes or no? And if it's no, I will try to help and solve it. But I'm under time pressure, so I prefer if somebody else solves this, finds the strategy.
Okay. Just no. There is actually some interesting thing. If we prove this inequality, also, it's kind of a very delicate proof because we need to use Romashchenko trick twice, which is especially outrage, just something completely stupid. We make twice. This makes things independent in different ways, but so it's quite maybe it will give some complicated combinatorial stress. It means that combinatorial translation for this game may be more difficult, but at least one should start with the easy game with in 2 dimensions.
Okay.
So maybe next time someone could explain the strategy, but if not, we will put Bruno's talk at the end of January.
Okay. I think that we can skip next time because I will be on the plane.
What you will do, be?
On the plane.
Coordinate plane, or
No, just plane, which is aircraft.
Where you will go?
St. Petersburg.
Okay. Yeah. Just recently, a plane from St. Petersburg to Moscow landed with one engine. So before going to Petersburg, you should check that both engines work.
Okay, I will check for sure.
Yeah, because now you cannot repair the engine because all the parts are unavailable. So it's important to check. Okay, so sorry, I should say it more clearly. Somehow all the story with Zoom also.
No, it was okay. So
yeah, it was very nice talk.
The problem was clearly, the challenge was clearly formulated.
Yeah.
So I'm leaving now.
Yeah.
Bye bye.
And maybe the day in 2 weeks, maybe Lyosha Milovanov finally will give a talk, which he promised for long ago, explaining what this Hirahara and other were doing. But let's see.
But also the nice talk about decision trees. He has some nice result about NC1 completeness.
Okay, so what you are doing? Why you are under some strange roof?
in some supermarket or something like this. Yeah.
Sorry?
Sorry. Okay. Yeah, in the some supermarket. Okay.
Yeah, very strange supermarket. It's like it's more like бомбоубежище. But okay. Still in 2 weeks you should be ready to explain something interesting, whatever you want, but interesting. You have so nice like on the sun and in Portugal, so you should be we should hear you. Okay. Thanks.
Okay,
Thank
bye.
you. Bye.
Thank you. Bye.